In this video, we're going to take a look at electric power and also do a review of the new quantities that we've introduced regarding circuits, current flow, and electric potential. Power is a good physics 1 connection, and it's the rate of energy transformation. Energy transformations come to us from energy conservation discussions where work can become kinetic energy, can become potential energy. And then sometimes we have devices that can cause those transformations to happen. Like for instance, the engine in a car. So it does work to give the car kinetic energy, and it's not always 100% efficient. So a higher power engine will be able to make that transformation faster. And if we now consider what it looks like for electricity, energy is charge times electric potential, which is energy per charge. So energy is Q times V. But then if we're looking at a rate, we would divide by time, and Q over T is, of course, current. So this winds up giving us a new relationship in addition to Ohm's law. Power equals current times voltage. And of course, we can rearrange that by using Ohm's law. The joule as a unit of energy is actually a very small unit of energy. And we live in times where we're big consumers of energy, and also energy is relatively inexpensive. So the kilowatt hour, as mentioned previously, is a unit for measuring energy, even though it's got watts in it. But kilowatt hours is the equivalent of using 1 kilowatt worth of power for 1 hour. So in our household circuits, we have to be careful about the rate at which we use energy. And in order to provide safe situations, we have a number of different devices that can control the flow of electricity. Now, fuses aren't used in houses very much anymore, but they are used in cars where circuit breakers are not very as useful. So what a circuit breaker does compared to a fuse, which a fuse just melts when too much current flows through it. And we have to avoid too much current flowing through our household wires because that can cause a fire. And the worst thing about it is that the fire happens inside the walls. And you won't see any evidence, no smoke or flames inside the walls until frequently it's too late. So controlling electric current is a little bit safer with a circuit breaker. And what a circuit breaker does is it allows all the current through that particular circuit, and you might have in your apartment or your house anywhere from 5 to 10 circuits or more, depending on what your heating situation is like. But the current flows across a bimetallic strip that makes contact and completes the circuit. But this bimetallic strip, when heated, when a lot of current flows through it, will have one metal that expands faster than the other, and so it'll start to bend. And when that pen reaches this little indentation, then a spring will open up and contact is broken, and so no more current can flow. And so typically you can't just reset these circuit breakers right away because it takes a little while for the metal to cool off. And also it's got sort of a springy nature to it too. All right, well, that gives us a window into power. I want to stop sharing my screen for a second and go take a look at my document camera as we take a look at some of the quantities that we've talked about. And then we'll also take a look at a model because one of the things that we know that's essential is that we need to have a way of visualizing the difference between voltage and current. That's probably the biggest conceptual barrier for new students. So let's think about what our quantity is, and then right next to that, we'll write down our definition is. Okay, well, let's suppose our quantity is energy. And so our definition of energy is what we use to make transformations in order to get useful work. Whether it's lighting up a room or getting a motor to do something. And then we should also talk about what kind of symbol we're going to use in order to represent that quantity. And then also we should always talk about units. All right, so that's what energy looks like. So another quantity is electric potential. And this is energy per charge. We saw, since we're talking about that, we should talk about charge. I can't spell. And charge, by definition, is the carrier of electrical energy. Let's start filling in some of the other pieces here too. So for, as far as a symbol, we could just write E for energy. Electric potential is V and charge is Q. So that's how they show up in formulas. And for units, J for joule, V for volts, and C for coulombs. Okay, good. Now what else do we know? Current flow. So current is rate of charge flow. Symbol is I. Units are A for amperes. And of course, power. And that's rate of energy flow. And the symbol is P. And it's abbreviated with the letter W for watt. Finally, resistance. Lots of new vocabulary in this chapter. And the definition of resistance is that it's the degree to which it holds back current. So let's suppose an obstacle to charge flow. And abbreviation is R, and units are ohms. Now, that's great. We have this nice long list, but we know that we can navigate between these symbols by identifying some key relationships that exist between them. So one is energy and power. So energy is equal to power times time. And Ohm's law is another. Voltage equals current times resistance, which sometimes you see represented as a graphic where V is in the numerator and then I and R are down here. So that if you cover up R, R is V divided by I is V divided by R. And the power relation, again, we can put P up here and then put V and I down here. And that gives us really quick access to the algebraic permutations of the power relation, I equals P over V, et cetera. Now, let's take a look at a model. Because the way electricity is set up in your home or your apartment is set up as an energy distribution network. And it's really helpful to have a model in your head to help connect to, because it's really easy to get turned around and confuse voltage and current. So let's think about an example, an everyday example that you can kind of visualize, right? Because a lot of these electricity concepts are very abstract and hard to visualize. So let's further reveal, let's talk about Amazon's distribution network model. So the thing that is trying to be distributed in our home or our office or apartment is going to be energy, but the thing we want to distribute with Amazon is packages. And so the carrier of the packages are going to be trucks. Now, electric potential, energy per charge. So this is going to be packages per truck. And rate of charge flow is charge per second. So this would be, maybe we're thinking about the warehouse, and maybe the warehouse monitors how many trucks per day they send out. So in order to deliver the same number of packages, you could either have a lot of packages on a few number of trucks, or a smaller number of packages on a larger number of trucks. There's an economy to either one. So power would be a measure of the success of that warehouse in packages per day, assuming that that's something you're trying to maximize. And then here, when we get to resistance, it sort of breaks down a little bit. So let's go over and we'll take a look at a simulation here where we kind of elaborate on this model. And so I'm going to share my screen and we'll take a look at a simulation I've got going over here. Currently, I have it set up so that we've got a 12-volt battery and then 2 light bulbs, 4 ohms and 8 ohms, 4 ohms and 8 ohms, but they're in 2 different configurations. And I've got it set up for a conventional current right now. I can switch it over to electrons if you want to think about trucks. In this distribution network, all the trucks they make visits. So this is places where packages are dropped off. But the trucks go to one location and then they all go to the other location. And this is called a series circuit. And if I grab my voltmeter, a voltmeter is going to measure how many packages get dropped off. So this is saying that 8 packages get dropped off at this location. And then this says 4 packages. So trucks start off with 12 packages each, and they drop off some here and some here. But the total amount that they drop off has to be the same. So in a series circuit, the source voltage is equal to the sum of the voltage drops across each individual. But the current is the same for each one. If we wanted to measure current, we can go ahead and grab an ammeter. And remember, to measure current with an ammeter, we have to install it in series. Like that. Okay, and so we get 1 amp altogether. So 1 amp or 1 truck per day, if you will. So maybe this is like more like a remote community. Now, if we take a look at what's happening over here, we can see that the current is flowing faster through the 4 ohms. Over here, the main difference between the two, the current is the same between through the two, but this one, the 8 ohms definitely looks brighter. But when I come over here, the bulb with the lower resistance is brighter. So that brightness would correspond to power. So we can go ahead and cut this. And stick it in an ammeter. And we can do the same thing here. And connect everything back up again. There, and now we can see why this one's brighter. Because it has less resistance, there's more current flow through it. So all the trucks start off with 12 packages. Some of the trucks go this way and some go this way. The ones that go this way go faster, like twice as fast, because the resistance is twice as more. And then we're going to use this analogy when we start taking a look at problem solving, and those will be the next videos.